Okay, so this is February 19th, nonlinear. So we are continuing sliding mode, right? You did see a simulation last time of inverted pendulum controller, right? So the equations were like x1 dot equals to x2, and x2 dot was, I think, h of x plus g of x u, right? So inverted pendulum equations can be put in this form. H of x is not known perfectly, g of s is also not known perfectly, and I think we came up, so you choose the sliding manifold s equals to a1 x1 plus x2 equals to 0. So we have shown that if you once you come on this sliding manifold, you slide into the origin, right? And your controller u was, I think, something like minus beta x sine of s, which made your v dot to be less than equal to negative of I think beta 0 or mode of s, right? So this controller basically guarantees that your s goes to 0. That means you reach manifold, and then at the manifold you then slide to 0. Okay, so that was the whole idea. But I don't know if you saw the chattering effect. So because let's say we are using an s function or something which is not able to, it's a numerical approximation, right? So you're not exactly going and stepping on the manifold because of the inertia errors. You cross that, and then suddenly because of the nature, it was like what, u equals to minus 4 of sine of s, right? So you come with full force back again, and then again you overshoot. So basically there is a lot of chattering, and that chattering will increase if you add noise to the system. Let's say some of your states are noisy, you don't exactly have the perfect knowledge of state, then also there will be chattering. Okay, so how do you reduce chattering? So there are a couple of methods. So first of all, the reducing chattering is because of two things. One is because of this quantity, which is the gain, right? So you should reduce, you should not, like what we did here in the first shot for the simplification, we cancelled almost everything, even it was known, not known. So you should apply this maximum cancellation only to the quantities which are not known to you. If they are known, then have them continuous, like cancel in a separate way, rather than putting into the inside of the sine function. I'll give you an example, things will be clear. So the first objective is to make this smaller. Once you make this smaller, chattering amount will reduce because the force by which you're coming back and forth will reduce, right? And second thing, the main reason for chattering is this also. This is a very discontinuous, right? Like +1, -1, +1, -1 kind of controller. So if we can come up with some kind of a continuous form, because the problem, where is the chattering problem? Mostly here, close to the boundary, right? Close to the manifold, right? That's where the chattering problem is. So until here, so what the idea is, you use a saturation function such that outside this boundary you use sine function, and inside this function boundary you use a continuous function, basically. Okay, so that's the idea here, and that can happen in one single shot using saturation function. I'll show you how that can happen. Okay, so so let's formulate the problem here on next page. So let me first define what is a saturation function, right? So what is a sine function? A sine function looks like this: sine of y, sign of y, right? So this looks basically like this, right? So -1 +1 basically, and this is your y. So that is the kind of function right now in use, and there is a saturation function. We call it saturation of y over epsilon. Okay, so there is another quantity called epsilon. So let me make a picture first. So that again is y, and this is this function here. So basically the idea is instead of saturating, so in this region, this is basically continuous. This is equal to s. The slope is equal to 1. Okay, so that's the objective. Yeah. So how it is defined? Saturation of y is defined as as equal to, so this is input. Now you're, instead of sending y, you're sending y divided by epsilon. Okay, so to scale it up, so you're saying if it is equal to y, if so input, so this input can be y by epsilon or just epsilon also. So any input, if that is if mod of that is less than equal to 1, so this quantity is 1 right here, +1, and this is -1, right? So between +1 and, if your values of y are between +1 and -1,
The slope is itself.
so yeah, it's equal to y, right?
Or the value is itself. The slope
And
is itself.
otherwise it is sine of y. So that's your saturation function otherwise, right? If y is greater than 1, both sides, absolute value of y is greater than 1. Okay, so that's the objective. Now if you put an epsilon here, see, so then it was divided, like epsilon is 0.2, 0.3, whatever that is, and that can change the this region here. Okay. Okay. So let's see how does that affect our so this is the case, but when epsilon is there, it will be y by epsilon, and this will be y by epsilon, right? So okay, so the y, when y by epsilon is equal to y by epsilon, okay, if you put epsilon inside. So let's see what is the effect on our Lyapunov when we use saturation, and it will make things clear. So this is how it looks like. Let's say this is our picture. So this is our sliding mode, right? This is s equals to 0 slope, and this is s minus epsilon, and this is s plus epsilon, right? So basically in this region here, okay, so that's the region. This is epsilon boundary. So now let's start. So what happens when I'm here? That
You have that aggressive negative.
yeah,
forward
so
there.
then in that case my u equals to minus whatever that beta x sine of s, right? Because here I'm applying sine of s outside that boundary. SIGN s, right? And if you remember our v half s squared thing, and v dot when we apply this controller was less than equal to minus some coefficient beta 0 into g0 beta 0 s, right? So what does that imply? That you will in finite time cross this boundary, right? It is pushing you to make this quantity is, when you are applying this, will guarantee that s is going towards 0. Your trajectory is moving towards s equals to 0, right?
So how do we show that it goes there in finite time?
Now I can show that. Yeah. Yeah. We have a mathematical proof. We can show definitely that it goes in finite time there. Okay. So let me show that to you. First, because it is negative, the trajectory is approaching to this quantity, and it can be shown that it reaches there in finite time. Okay. So that's outside. So that means it is attracting, right? That means this controller make sure it doesn't matter where you are kind of being attracted towards that pipe, that boundary, right? Now let's see what happens when you are inside that region. Okay, so inside that region s is not equal to 0 yet. S equals to 0 only at that place, right? So if you see our equation, what is s? S is equals to a1 x1 plus x2, right? And what are our equations? X1 dot equals to x2, right? So this is what? This can be replaced by x1 dot, right? So I can write s equals to, now s is not equals to 0, so s will come into picture, a x1 plus x1 dot. Okay, what is x1 dot now? X1 dot will be minus a1 x1 plus s. Okay, see, if s equals to 0, then I know that x1 will go, but right now in this boundary, so this controller only guarantees that you reach here. We don't know whether we reach on the s equals to 0 or not. So now we have to show that if you reach in this pipe, how close will you get to the origin now, right? That's the idea now. Because s is not 0, may not be on the manifold. So we have to now analyze when you reach inside this, how close you end up to the origin. Right? Is that making sense, what I'm saying here?
So why did we mention that epsilon in equation like?
Yeah, we will mention it right now. Right now, this is where your epsilon will come in now. When we start putting bounds, because now your s is bound. You know that here s is not 0, but it is bounded between plus minus epsilon, right? So that information will be used here. That s is upper bounded by epsilon, right? Because we know that pipe is epsilon because we are around. So that's good. Now let's plug it in v1 dot. What is v1 dot? So v1 equals to half x1 squared, right? So v1 dot is minus x1 dot, right? x1 dot, let's plug that in. So now v1 dot becomes minus a1 x1 squared plus s x1. Now I don't know if it reminds you of input to state stability or not, but it should. What happened here? There is an extra naughty term or bad term because of s not equal. If s equals to 0, what is the term? Negative term, right? Game over. If x1 goes to 0, and if x1 goes to 0, x2 will also get 0 because s equals to 0, right? But that's not the case. We have this term to deal with, and it looks like that u of x1, I don't know if it reminds you of that what should, now we are saying what condition, if you compare it with the input to state stability problem, we have to come up with a condition for x1 which will be a function of s, that what should be x1 greater than such that this thing is negative, definitely v1 dot is negative, right? So now we have to ensure that for what values of x1 this quantity v1 dot is negative definite. If it reminds you of input distributed, right, state stability. Now we can see that your x1 will come out to be, you will see that x1 is a function of some rho epsilon for which this is negative definite. So you will see that your x1 now will go below that bound. So that means you will come, you can make a kind of a rhombus kind of architecture here, something like this, where you can say your trajectory will come in. But yeah, let's move forward with that thought. Okay, so now what I can do is, we have v1 dot was to minus a1 x1 squared, which is plus x1s, we can say, which is less than equal to minus a1 x1 squared plus x1 mod of x1 into epsilon, right? What is the value s's value? What is s bounded by? Epsilon, right? Because now we say that we have already come into this, that means s is between plus minus epsilon, so I can plug that in, because this is always negative, this quantity is creating a problem. So now we can do another further step, which is you can break this part again, doing that 1 minus theta part, saying take some negative parts in the sideways. So we can write like this, saying, hey, it is less than equal to minus 1 minus theta 1 a1 x1 squared, and minus, so that is minus plus, so minus theta 1 a1 x1 squared plus x1 into epsilon, right? Same, nothing, just added a 0, right? So this and this is added to 0, but this is theta 1 is between 0 and 1, right? Between 0 and 1. So that means this is negative definite, as long as we can show that this is negative, right? So to do that, we can say minus theta 1 a1 x1 squared plus x1 epsilon is less than equal to 0. And then basically we are saying this condition is met. So if you take this side, and so it becomes like this, it becomes theta 1 a1 x1 squared, same thing, right? Squared, so positive, I can write it like this, it is x1 epsilon, and then x1 basically is greater than equal to epsilon over theta 1 a1. So as long as, theta 1, as long as x1 is greater than epsilon over theta over a1, we are guaranteed that your v1 dot is negative definite, right? That means x1 will keep decreasing until you hit that boundary, right? So in fact you can go and find out that the trajectory so from this you can find a bound and actually show that your x1, so what does that mean from this picture's perspective? Let's draw again. So let's say this is our s equals to 0, right? Going from the origin, this is our epsilon boundary, right? And this is, let's say this is, let's say which graph. So this is our x1, this is our x2. Okay, so we are saying first we are guaranteed that we will reach here, right? When we reach here, we know that this is x1 square is negative definite as long v1 dot is negative definite as long as this is true, right? So that if you want to draw this boundary, right, this here, let's use green color here. So let's say this is that boundary. So you can see this boundary here. So basically we are saying as long as x1 is greater than this quantity, right, epsilon over theta over a1 plus minus, this is absolute of x1, right? So you're saying as long as x1 is greater than this quantity, x1 is going to decrease. Yeah, because v1 dot is minus a1 minus theta x1 squared, right? a1. Because of this your x1 trajectories definitely will. So you, let's say I came here, but then it will start decreasing and come here, right? So now you can also find an ultimate bound from the same theorem, which says that x1 will always be less than because if it is greater than, that means the lower bound will also come to be theta 1 a1, means x1 will enter here and it will not go out of this. So the upper bound on x1 basically is e over a1 theta 1, right? So now you can use this to find what should be what should be the bound on x2, right? How do you find that? Our s equals to a1 x1 plus x2, right? And so x2 equals to s minus a1 x1, right? And we are saying x2 should be less than equal to mod of s plus a1 x1, right? So now you know bound on this, which is equal to epsilon, and which is equal to plus a1, and what is the bound on this, which is epsilon over a1 theta 1. So basically this cancels out. So basically it is your x2 bound is also there now. So basically you will also get a boundary on x2 that you will reach somewhere within this triangle. So your trajectory will kind of enter this up here and it will stay here. Now depending on how big your epsilon is, this boundary, how close you can get to the origin will be defined. Because if you leave math apart, means it's not that you just have to derive it and see it. But that's what we are saying. The first guarantee is here, and within this also we are guaranteeing that this will enter an ultimate bound close to the origin, even though we are not using the exact sine function. And this makes close to this because what is the function? It is just, instead of sine s, it is just s inside this. So you are using a continuous function rather than plus 1 minus 1. You are using a continuous. So trajectory will be that chattering will not happen because now it's just continuous. Okay, so that's the kind of goal we have here. So we should apply this to the pendulum and see if it was visible last time, but let's see if we can. So let me also show you before we even move to simulation that question of reaching in finite time, right? Let me answer that question. And then region of attraction. So this is called region of attraction, if you will. Where is this thing I draw, right? So this, and then I think if you draw the extra boundaries also. So this here, whatever shape that comes, this is called the region of attraction. So your trajectories go and then go here, whatever direction it has to come. Yeah, so that's good. Like you can use. Chapter 14, 14, 14. Okay, let's show the so I'm showing the finite time arrival in that region, right? Finite time in which s goes to 0 if you use this what was that, u equals to minus g0 beta x sine of s, right? If you use that, your v dot was less than minus g0 beta 0 mod of s, right? So given this, how can you show that it will reach things in finite time? Okay, so what is our v? Your v equals to half s squared, right? That's what we are dealing with here. So let's assume let's assume a function w which is equal to square root of 2v. Basically, what does it mean? What is w? If square root of 2 into v is s square, basically s, right? So then what is w dot? W dot will be, if you differentiate this, it will be v dot over 1 over root 2v. Okay, and if you plug in the values of v dot, what is v dot? V dot comes from here, which is minus g0 beta 0 mod of s divided by 2v is nothing but s squared, and equals to minus, and it's always positive. You cannot, because if you see why I'm instead of writing s, why I'm writing this, because I'm showing that s is always a positive quantity. So we can write z0 b0 s over mod of s, right? So this cancels out. Your w dot is basically equals to minus g0 beta 0, which is a constant, right? So basically saying x dot equals to minus 2, something like that, right? Now having this equation, what is the you can solve this ODE very easily, right? It says, how do you solve this equation? If somebody gives you dx by dt equals to minus 2, what will be the solution for this? Not e. In this there is no e. I think it's just saying x equals to minus 2t plus some constant, and that constant at t equals to 0 is x of t0, right? So x of t0 minus 2t, right? That's the solution, right? So similarly we can write a solution for this also, right? What is omega t, which is a function of s, of course. Same, using this will be minus omega t0 minus g0 beta 0 t. That I can solve for this, right? I can say if this is equal to 0, I can get a finite time. So this is going with a constant slope, decreasing. When will this be equal to 0? So you can solve for that, right? Omega 0 divided by g0 b0. This is the velocity at which is increasing, so it will be t star, I believe, right? So that's your finite time. So it goes, actually you can also find what finite time. This is how you will get the time. The s goes to 0 in this much time, because it is going, you are showing that it is at least going with this rate, negative rate. When you're at least your rate is defined, your minimum rate is known, then you know that at least within that time you will cross that s equals to 0 boundary. Got it? So let's okay, so both, yeah, right, using saturation function also mathematically we have shown that even though we don't exactly reach to the manifold, we can still reach within the area of attraction, which is defined by that epsilon value. How small or big you choose depends on how big, what is your system dynamics and all, how much or big of epsilon you will need to get rid of chattering. So then epsilon becomes a tuning parameter basically, right? Okay, so let's go to simulation and play with it and see if we can basically get rid of this. So let's see what assignment should I give for this. I think I have an assignment. Let's see. We have an assignment for this homework assignments. Adaptive control homework 6. What is this 6? This time attach the simulation files and figures when submitting the assignment. So 14.1, 14.2, 14.3.
More book work.
14. No, but this time it is animation.
Okay, okay,
Right?
okay.
It's designing a controller now.
All right.
To design a controller.
Okay.
And then you implement it. And then we'll go to bigger problems. You're just starting. There will be a UUV, but sliding mode control problem. So let's see. So yeah, this is your homework number, next homework. So anyways, let's see if our MATLAB is open. Change folder. So if you see, that's our U2, right? So instead of, so this is my saturation function implementation, right? I'm saying if S by epsilon is less than equal to 1, absolute means, then let's use minus KSE, we can. So instead of 4, so K is 4, right? So if you remember in last time it was minus 4 sine of S, right? This time we are doing minus 4 saturation of S by epsilon, right? Saturation of S by epsilon. That's the controller we have. Control S. Okay. Or maybe let's call it U2 so that we can separate it out. U2. Right now we are just going with the same function and see what happens. Sliding mode. So epsilon is 0.2. You can come reduce. We'll see the effect of increasing and decreasing the epsilon. You cannot have a very small epsilon. That chattering. Then again, if you're too close to the manifold, then that chattering problem will be there. Takes forever. So I think after this assignment, Yeah, maybe one or two more book assignments, but okay. So parameter run. So right now normal function, right? So I think you saw the trajectories. The so see this was the reaching phase, this small portion, and then there is chattering. Will okay. You're sliding to the origin of slowly, right? You're sliding to the origin here. See, but there is chattering there. Okay. So if you want to see that, so you will see if you see u. That's like this is your control, right? So plus plus 4 minus 4 plus 4 minus 4 plus 4 minus 4 is what it is doing, right? And yeah, it can show you that you're reaching 0 0 and 0 0, right? So that means you're reaching at the origin, not a problem. And this chattering, like this is the case when we do not have any noise or something. If you put noise also, this chattering will increase significantly. In fact, this one increased significantly. Right now, you only see it here, but this, see, at the end it increases. But these oscillations might increase if you have noise or something, because it will take some longer time to turn back, and then again longer time to turn back. Okay, so that can happen. So now let's see, use a saturation function with very small one. Where is my controller? So let's say 0.01. Let's start with 0.01 and let's output IU2. Okay. So still chattering, right? So 0.1 is not good enough.
And point one, you changed the
But
value of which?
0.01, epsilon was 0.0.
Epsilon, okay.
Right? So we are saying the manifold, that boundary thing is
Yeah,
not
right, yeah.
Okay? No. So,
Yeah, I just didn't see what you changed.
so again, let's go and change the epsilon. So let's say epsilon really high. If you say epsilon 0.1 or 0.5, let's say. Right. So that's really high epsilon. And where's my trajectory? So see here, much smoother. But you will see that the pendulum will be not vertical, but near the origin in that area. So we can only guarantee that this will reach that close to x1 to b0, right? So you'll see that your pendulum is not now straight because we are using such a big epsilon. But it made your trajectory smoother, but you're not. You have to compromise on the tracking error. That the pendulum, but you can give that bound how far that will be. You can compute actually that how far that theta will be if you choose this epsilon, right? So, but if you see the trajectory here, it's pretty normal. So you see that it comes inside and then goes near the origin. It's where that thing, that ultimate boundedness come, that your x1 has to be greater than this epsilon over this, then only that is negative. So you reach up to that point, and then so that's why you will see that it will not, in fact it goes ahead of 0, right? So because that's a boundary here, the absolute value, so it goes little that side. So that's the case. So we can choose epsilon little smaller, point 1, let's say. But let's check the trajectory first. This one also, right? What the controller looked like. See, the controller is so smooth. Goes and stays at 1. So. See, you're always applying some control input. That's the bad part of it. But it is much smoother. So let's see what happens when we do epsilon 0.1. Still chattering is there. So that 0.1 is not. I want to find a number which we are just, So, but the not good, good enough. So
That's kind of asymmetric there.
yes, what happened? Why did it go from minus? What is that? -4. So yeah, because of the saturation function, it is not going -4 plus 4. So this side it is only whatever that
-1
one value or
or
something,
2,
and
yeah.
then here it is going up to 4.
Yeah.
So now if we increase it to 0.2, because here is just giving that epsilon which side it hits is not. Yeah, I think 0.2 cuts a good margin of number. So 0.2 you see there is no chattering and it should be close enough. So that boundary now because your epsilon is reduced, your boundary, upper bound on x1 also reduces. Okay, yeah, it still banks on the other side a little bit, but good enough. But yeah, this kind of hits the one. Initially it goes with -4 because it was outside that S, right? And then when it reaches, then it uses that. Okay, and you should be able to verify your bounds and everything, like you numerically compute it and see if it is verified in the simulation also or not. Okay, questions?
So why is that value 1 on the asymptote?
Yeah, I think
Why is it
what was that? So it was -4 into S by epsilon, right? So inside the boundary, what is your controller? It is -4 S by epsilon, right? That's your controller actually, isn't it? So maybe this whole number S was what? So epsilon is 0.2, and what happened? Whatever that multiplication happened, S became negative, I think, such that this whole multiplication would have been -1/4, I believe. S by epsilon. So S goes and saturates at 1/4. What is 1/4? So 0.25, right? Is it 1? No. So total is 1/4, right? So S by epsilon is 1 minus 1/4. So and epsilon is 0.2. So what will be S? Minus 0.2 over 4. So basically minus 1 over 20. So that is what, 0.05 or something. So that's where S settles down, that close to it, and that's why the controller is -1 or 1. So your question, why does it? So I don't know what happens inside, right? We can only give bounds. So, but S goes and settles down on a value, and then. Okay. So I think we can leave here.